So it was really a connection of entropy to something that is more concrete, which is the microscopic, and by microscopic, I mean nanoscopic or smaller nature of matter, where we have particles, which are molecules and atoms. And so we were looking at the Joule-free expansion, and what we found with the Joule-free expansion using a lattice model, right? And that lattice model is just a very simplified model that we can use. We have a lattice and we put particles on that lattice. Okay. And these kinds of models have been used in the field of statistical mechanics, statistical thermodynamics, in physics for many decades. And they're very powerful because they allow you insights as to what's going on. As we just saw last class, it gives us some insight into what entropy is. And in particular with biological systems, you get a lot of insight using lattice models. So with the lattice model, we saw, let me just scroll back to our initial state where we have particles in a box where we have n sites, where n is this capital N, okay, and that's a proxy for volume, if you will, in our macroscopic case for the Joule-free expansion. And we have all these constraints that I'm not going to go over again, but they're available on the uploaded lecture. So they're very important constraints and conditions that we impose. All in these constraints and these constraints that we impose allow us to use mathematical approximations, namely Stirling's approximation, as well as to mimic the physical system that we're trying to model, which is an ideal gas at constant density, okay? So these constraints serve two purposes, and they're very important. And this is an indication of how mathematics and the physical world are connected. And this is why physics is so heavily dependent on mathematics, because you can use the language of mathematics to recapitulate, which means model reality to a very high precision, if you will. Okay, and you have to be very, very careful how you do that. So, and it takes a lot of energy and focus and discipline to do that and to understand it. So we did this, and then we went to our second equilibrium state, which is this case where we have twice as many particle sites, and that's again a proxy for twice the volume. And we have similar constraints. And then we were interested in finding the number of ways. And it's very important to keep in mind that this is an isolated system again. The Joule-free expansion was isolated, and the particles are indistinguishable. Okay, so there's no way you can distinguish, if you have n particles, the first particle from the nth particle. There's, little m particles. And we were interested in this thing called W, which is the number of ways you can arrange those little m particles into the sites that you have in your lattice. Okay? And this is a very well established solution. And you can use go ask a mathematician who studies combinatorics. He will give you she will give you this information. And the expressions are here. They're very simple expressions, involve factorials, where anything factorial, for instance, 6 factorial, is just 6 times 5 times 4 times 3 times 2 times 1. And 0 factorial is 1. In fact, you can prove that using series expansions, but we won't do that today. That's a different thing. So when you do that, you can get expressions for the W's, which are the ways you can arrange these indistinguishable particles. And these W's are for indistinguishable particles, okay, indistinguishable things that you place on these lattice sites. And since we're dealing with really large numbers because of this constraint, we said that we'll just deal with the logs of these very large numbers, because the logs are the exponents, and then the exponents are much more tractable. You can deal with the exponents. And so we decided to use logs. And in fact, that doubly helps us because we can now use our approximation for logs when we have very large numbers and we take their factorials, which is called Stirling's approximation. And this is Stirling's approximation. Okay, it's a general mathematical result, so you can apply it to any system where you have log of very, very, very large numbers taken to factorials. And so we went through and we worked out our logs for the W1 and W2, and I'm not going to go through all of those details again. This is all online. But what we found at the very end is that we saw that log of W2 minus log of W1, okay, was related to, or was this expression right here, m times the log of 2. And that 2 comes about because we have a doubling of the sites, capital M, in our lattice between the initial and final states. And again, m, this little m, is the number of particles, not moles, but the number of particles that we have. And the interesting thing that we found, or we related this to, was the fact that in the Joule-free expansion, which this lattice model setup is mimicking as best as it can, we found that for the Joule-free expansion, okay, which is an isolated system, ideal gas, expanding irreversibly. Okay, so we found for this case that delta S for the Joule-free expansion was n, where n now is the number of moles, times R, the universal gas constant, log of V final over V initial. And in the case where if V final is equal to 2 times V initial, okay, this delta S is just n our natural log of 2. And that was kind of interesting because it relates to this natural log of 2 up here. Okay, where we have some term that is a term that's involving what you have. In this case, little m is the number of particles. In this case, this is just the number of moles, okay? And R takes care of the units, times log of 2, times log of 2 in both cases. So the insight, or the conclusion that we were able to reach, is that at a microscopic level, or at a very fundamental level, one of the very fundamental levels, S is related very directly, in fact, directly, I don't know why I said very, is related directly to W. And I just use W as a letter. W doesn't have any absolute meaning. I could have used Z or P or whatever I wanted. It's just a representation of what something really is. And that W is the number of ways a system can be realized. Okay? And by realize meaning, how can you find the state of that system, right? If you were to have this microscopic camera, remember how to motivate entropy, I use this idea of a camera or a movie camera that you could actually see all the particles and take a movie. And remember I said you could take the movie and then play it forward and then show your friend, but play it backwards and your friend wouldn't know the difference because of the symmetry of the laws of physics. So W is this, the number of ways that exist to find the system at equilibrium if it were left alone. Okay, so it's the number of ways a system can be realized, and by realized, I mean how you would see it. How, if you had this camera that could continuously take a movie of the system, how many distinct ways would you find that system in? Or how many different arrangements would you find the system in if you could peer at the system at the level of atoms and molecules? And this actually even goes down to electrons and subatomic particles. But for the moment, since we're dealing with chemistry, and chemistry can be dealt with more or less for the problems that we're interested in using atoms and electrons, we deal with those particles. Okay, so W is just the number of arrangements of a system at a microscopic level if the system is left isolated. Okay, any questions on that interpretation of what W is? Okay, so it has nothing to do with chaos, or it has nothing to do with disorder. Okay, uh, and you can see here that those words don't really mean anything because we define W in a very precise way. You cannot, there is no way to confuse what W is. You can't, there is no way to connect W to chaos because I told you what W is. I told you exactly what W is. W is the number of ways a system can be realized. I didn't say anything about chaos. I didn't say anything about disorder. Okay, so there's no way you can confuse what W is with any other term, with any other word. Okay, and I would further add any other arbitrary or ambiguous or vague word. Okay, so what we're saying is something very, very precise, and you have to keep that precision in your discourse when you discuss W. So since S is related directly to W, okay, we saw then that S1 you could relate to the log of W1. Okay, and I'm not going to write the expressions for the W's again because they're already presented above. And we saw that S2 was related directly to W2. Okay. And actually, this was M times log of 1 and M times log of W1 and M times log of W2, where M is the number of particles. And I remind you that this is the number of particles, not moles. Okay, it's different than moles, right? Through Avogadro's number. So in this case, then what we found is delta S, which is S2 minus S1, is equal to M times the log of W2 minus the log of W1. Okay. In terms of particles, which we can then also write as M times the log of W2 over W1. Okay. And we can put this here because we're missing one thing at the moment, okay? So delta S, I'm gonna put this here, which means approximate, and I'm gonna make this an equal sign in a little bit. But right now, because I'm missing something, because what we saw, so this is with the lattice model, okay? We got this, and then with our delta S from the integral of dq reversible over t, we saw for the Joule-free expansion. Now I use the equal sign. It was nr natural log of 2. Okay, and this is what we saw here is m natural log of 2 in our case. Okay. So it turns out that we can make this equality, okay, because of units, because we know that R has the units of energy per unit mole per unit temperature. Okay, so it could be joules per mole Kelvin. So R has units something of joules per mole Kelvin, or you can use whatever energy units you want, but that's one set of energy units. You can have units in terms of pressure as well. So when we multiply this by moles, which is little n, we would get units of joules per Kelvin. And since the log of something doesn't have units, delta S, or S then, would have units of energy per unit temperature. Okay, so the units of S are energy per unit temperature, in this case, joules per mole K. Okay. So with our lattice model expression, we see that we have particles multiplying log of 2. So this delta S that we almost have is having units of particles, and log of 2 has no units, so it's really just particles. So we have to figure out some way to make this consistent. Okay. So how would we go from particles to some energy form? Well, we can say that, well, I'm not going to derive this. You can derive this from a very fundamental point of view, but I'll just present it. So Boltzmann, when he came up with, when he was doing his work with statistical mechanics and trying to understand entropy, and other things from a microscopic level, he came up with the Boltzmann constant, which is called Kb. Okay, and this is the Boltzmann constant. Okay. And it's a relation or a connection between the particle nature or the particle view and the mole view. So if you want to have a macroscopic view of matter or a particulate view, a very, very refined microscopic view. And it turns out that it's related through R. So it's time, and the relation is R is equal to NA, where NA is Avogadro's number times the Boltzmann constant. So this is Avogadro's number. Avogadro number, and this is the Boltzmann constant. Now, the derivation of this requires a lot of machinery, so I won't do that. Okay. But you can see here then that KB, if we rearrange this, is really R per particle, because we know Avogadro's number is the particles per mole, and A is 10 to the 23rd, and that the units of that are particles per mole. So we see here that K sub B with the Boltzmann constant is really R per particle. Okay, and so since R is per mole and NA is per mole, the per moles cancel, right? So really this is just joules per mole K. And then in Avogadro is number of particles per mole, right? So we see here that since we have a per mole on the top in the numerator and we have a per mole in the denominator, the per moles cancel. And what we're left with then is joules per particle K. Okay, so now so K is really just R per particle, right? That's all it is. So R was joules per mole K. K sub B just turns out to be joules per particle K. Okay. So going back to our expression for delta S, which was NR log 2, and really, if you remember, this was NR natural log V final over V initial. If we take our macroscopic view, right, we can say then that R, we can do some, let's see, we'll use NR, but we can say that R is NA, KB, times natural log of 2. So all I've done here is substitute my expression for R. Okay, right here is NaKB. But what's N times Na? N is the number of moles, and Avogadro is particles per mole, right? So this gives me M times KB, natural log of 2. Right? But what's KB? What are the units of KB?
Joules per particle Kelvin.
Right, joules per particle Kelvin. And so if I multiply M times KB, what am I getting?
Joules per Kelvin.
Joules per Kelvin. That's exactly right. Okay. So we see here then that in both cases, we're getting something now that's consistent with energy in terms of the units as well. Okay, so in this case, we get joules per particle Kelvin. And in this case, we get joules per mole Kelvin. But we're multiplying KB by M. So this is just, when we multiply it by M, we just get joules per Kelvin. And in this case, what we get here is joules per Kelvin, right? So our units come out to be the same when we introduce this thing called KB. Does that make sense? Did I confuse people or again, I want people to be clear. So the units now become consistent, both entropy from the microscopic description and the macroscopic description using dq reversible over d come to have the same units once we define something called the Boltzmann constant. And this Boltzmann constant can be derived. It actually naturally falls out of the derivation through a statistical mechanical analysis of all of this, but that's something that would be covered in a graduate course. I'm not going to cover the derivation of that here. Okay. So the point here is that both microscopic and macroscopic views have the same units for entropy. Okay. One uses R and one uses K sub B. Any questions? So if I were to say now then S, if I wanted to remove this per particle, right? If I wanted to just say this is per particle, what I would do then, delta S, I would just divide it by M. And that turns out to be KB natural log of 2. Okay, everyone follow? Please chime in if you are not following. This is very important. So, okay. So this is delta S. Okay, and I'll write this a little bit more explicitly. That was just KB natural log of W2 over W1, which is equal to KB natural log W2 minus natural log W1. I'm just unfolding, unwrapping everything, which is just KB natural log W2 minus KB natural log W1. That was delta S over M. Okay, so this is our now S per particle. And so what we can see here then, that this guy must be S2 per particle, and this guy must be S1 per particle. And those are just per particles, okay? So we're just gonna say that, all right, we'll define now our entropy from a microscopic point of view, a very insightful point of view, as S is equal to K sub B natural log of W. Okay, and this is for an isolated system. And this is a very profound, and again, for this course, this upper level course, 400 level course, this is one of the most, this is like a pinnacle result of this course. S is equal to KB log W, where W is the number of arrangements you can find at the microscopic level for an isolated system, okay? So again, in this box, there's an equation and the associated words that have to go with that equation for all of this to make sense, okay, at this, so for the sophisticated level and understanding of entropy. So in an isolated system, the entropy now is defined as this constant, which gives us the proper units, times the log of the number of arrangements at the microscopic level that you can find the system in. Okay. Since an isolated system has constant U, many people interpret this, and this is another interpretation which you may have seen, is that it's the number of ways, entropy represents the number of ways you can have energy, which in an isolated system is constant, being dispersed amongst the particles or amongst the elements of that system. Okay. How many different ways, with each one of those particles or elements of the system carrying some component, some amount of that energy, which is constant, how many ways are there to distribute that amount of energy? Okay. That's what this entropy is in another interpretation. But this is the definition then of entropy. And so this W can be anything. In this case, for the lattice model that we chose to use and the way we approached it, it was this combinatorial factor. Okay, so in this case, W, right, was n factorial for the initial state over n minus m factorial times little m factorial. But this is just one specific case. Okay, this W and this definition of W that we use, or this model for W, isn't universal. It's not universal. Okay, and as an example, okay, I'll say that W is problem or context. W is problem or context dependent. Okay, keep this in mind. It's not always applicable. So you have to understand what the problem is, what the system is, and then ask yourself, okay, how will I determine the number of arrangements of a system? And so a very easy example of this, okay, is let's say you have a polymer, and a very simple, proteins are polymers, and these kinds of lattice models have been used historically to study protein folding. Okay, but we're not going to go that deep. We're just going to use a very simple model for a polymer, right? It's just going to be a chain. We have particles, they can be atoms or whatever you want to call them, with bonds. Okay, that's all we have. So we have bonds connecting the particles in a polymer. And the thing that we're going to focus on, right now, in this case, you can imagine you have this long polymer. We've simplified it, but don't worry, don't make it complicated, because all we're after here is a concept to further refine our understanding of entropy at a high level. And so if we have this polymer, which is just a bunch of beads connected by bonds, okay, we can say that each bond will allow a rotation. Okay, and perhaps you've seen this in your organic course or some other course where these things are called torsion angles or dihedral angles. Okay, or if you've built models, perhaps even in high school, where you put together these things, and you can see that you can rotate them around bonds. So in a case like this, you would have a torsion angle or a dihedral angle. I use them interchangeably. And I define that rotation or that dihedral angle as this guy. Okay, so you need 4 atoms to define a dihedral angle or a torsion angle, right? And so in this case, that red curvy arrow represents a bond around which I can rotate. Okay, I can't really rotate around the first bond because it's just a bond, right? I mean, I could rotate the bond in space as a rigid thing, but really I need 4 atoms. And so the 4 atoms that are involved in this torsion are 1, 2, 3, and 4. Okay, so those 4 atoms are needed to define a torsion or a dihedral angle. And perhaps you saw this with butane, the gauche and the trans forms of that molecule. So in this case, this example I have, let's see, how many torsions? I have that one, I have this one, I have this one, and I have this one, right? Yeah. So I have 1, 2, 3, 4 torsions, right? I have 4 torsion angles or dihedral angles in this case. Okay. And the way for this very simple problem, we'll say that the bonds are rigid, meaning that there's no movement. We're going to make the problem very simple to illustrate a conceptual point. And we can do that, that's fine. So all the bonds are rigid. Okay. And all the angles are rigid. So you can think of the first 3 atoms starting from the left in this polymer chain. You might say, well, oh, like in water, right? You might have some wagging. So there's an angle. My elbows are the two atoms, and then the vertex is the middle atom. And you might say, well, there's some wagging, right? Or motion between this angle. What we're going to say is that angle is rigid. It's just constant. So we have rigid bonds and we have a rigid angle. Okay? So the only thing in this polymer is really this rotation. When you have 4 atoms now, you can rotate around these bonds. And the question, just as we saw in the lattice model for the Joule-free expansion, we can ask the same model here for this very, very simple system. And that is, if we only allow for these torsions, these dihedral motions, okay, how many microscopic arrangements would you find this polymer in? And in order to answer that question, we only make one more constraint. And the constraint is that for around each torsion, you can only have 2 states. So around each torsion or dihedral angle, and this is a constraint, okay? This is something that we can either physically rationalize or we can impose on a problem that we want to solve. So around each torsion or dihedral angle, only two configurations or two states states are possible. And this might be, you might do some calculations using quantum mechanics to find out that there's really just two stable states around the torsion. And what that means is that you can have a cis-trans or an eclipsed, or what's the other one? I forget what the other term is. So what I mean is, let's say you have a bond between the two middle atoms. You could have the two end atoms this way. So that's one of the states of these two states around it. So this is your torsion angle, right? 4 atoms. The bond in the middle defines the torsion angle. So this could be state 1 around that torsion, or one of the possible choices around that torsion. And the other one would be this one, state 2 or configuration 2. I really should call them configuration. Configuration 1, configuration 2. And of course, for configuration 2, these two would be equivalent, right? There really is, right? So I could have these two, okay? But they're just the trans. So around this bond, sorry, around this torsion, there's only two states, whether they're on this guy or this guy, okay? So those are the only two things that are states that are allowed for each torsion angle. And so knowing that, as well as the fact that the bonds and the angles are rigid, you can actually enumerate. You can do this very simply. You can find out how many different ways you can find this polymer chain in. It's a very simple calculation because it's a very small polymer chain. When the polymer chains get bigger on the order of proteins and huge proteins and other things, the calculations become a little bit more crazy perhaps, but for this case, it's pretty simple, right? We can even talk through it. So for the first torsion, how many states are allowed? Let's just consider this torsion by torsion. So if we start with the left-hand torsion, how many ways can we find this first torsion? How many states would we see perhaps? Or that can we count?
Just 2.
2, right? Okay, so let's so the first guy has 2 states, right? So this is torsion 1, right? So we can have this guy in the cis. I'm going to call them cis and trans because I don't know what you've been introduced to, so I'll just use those terms, right? Okay, so now if we go to the second torsion, right? That second torsion is going to depend on what the first torsion is, right? So the second torsion, how many states are allowable for the second torsion? This is obvious. We stated it in the problem. It's a constraint.
Again, 2.
Again, 2. Okay, but our first torsion could be either cis or trans. So if the first one was cis, then the second one can be, again, cis or trans. So now, whoops, what did I do there? I don't know. But okay, if the first one was cis, the second one can be cis or trans. And if the first one was trans, the second one can be cis or trans. So this is torsion 2. Okay. And you can see now that we can do the same for torsion 3. My spatial perception is bad. I didn't draw it with enough room, but you can see here now for torsion 3, since I can only have 2 states, cis and trans, well, this guy can be leading to this third torsion, which is cis and trans. This guy is cis and trans. This guy is going to be cis and trans. This guy is going to be cis and trans. And this tree branches out until we get to the fourth one, which is this one. 1, 2, 3, 4. 1, 2, 3, 4.
So wouldn't it be 2 to the 4th power or 16th for the total amount of states?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah, Dr. Patel, sorry to interrupt your counting, but would it be 5 dihedral angles rather than 4? You appear to have skipped over one of the internal bonds.
Oh, you caught me. I'm very happy. You're paying attention. I did. Okay, so two people introduced, you are absolutely right, there's 5. So that's Michael, you're right. And then Sheldon, you are also right. So both of you are right. Thank you very much for paying attention and calling me out. So if I had 4, I would have had 16. This is what I showed here with this final counting. But now if I have 5, I'm going to have to add 1 more. So it turns out both of you are right. Let me just go back to a proper font, that for this polymer, in this case, W is going to be, what did you say, Sheldon? I think it was Sheldon, right?
Well, now it will be 2 to the 5th or 64 instead of 16.
Right, because in this case, that's exactly right. Both of you caught me. Both of you did well. So it's 2 to the 5th, because this is going to be a power law. And in general then, what's W going to be for a polymer of this nature with these constraints? It's going to be 2 to the
N, or total amount of bonds, angles, or torsions.
Exactly. Exactly. So you see here, W for this context dependent problem or this system is different than the combinatorial W that we started with for the joule-free expansion. And you both nailed it. It's 5 torsions, and the expression for W in this case is 2 raised to the number of torsions. Okay. All right. So it's 64. Yeah. If I'll whatever that is. You're right. I can't do simple math. Very good. I'm very happy that everyone caught me. That's exactly right. So again, this little example was just to highlight the fact that W is not universal. W is something that you have to read the problem that you're given and think about how you would formulate W. In some cases, it's very simple. In the combinatorial case, it might be a little bit more involved, but not too much. And of course, you won't have to memorize equations. You're always given equations that you may need that are complicated. So any questions on that? And so the point here was that W is context dependent. And again, S at the very fundamental level is W. Okay, and W is context or problem dependent. Okay, and so this is a way to get S and then delta S from a microscopic view of a system, right? In both cases, we had, right, with the polymer and with the lattice model of a joule-free expansion experiment, I hope you realize that in that case, we were thinking at the level of atoms and particles, right? With the polymer, we were actually thinking about atoms. And with the lattice model, we were actually thinking about ideal gas molecules or atoms at that level. When we did the delta S calculation with dq reversible over T, we ignored any idea or notion that there are these particles at that level. Okay, but it turns out that humans figured it out how to reconcile both pictures, and this was one of the triumphs of classical and statistical thermodynamics, that both of these merged to the same thing. A truly great achievement in human intellectual endeavor. And the other thing we see is that now S has a specific value. It has an absolute value. Okay, S is equal to KB log W. There is a value of S. Okay? There is something that, so we can actually make this argument that, let's say I have a polymer, okay, and for some reason, I freeze it. Okay, I freeze it to some very low temperature where now the bonds are frozen. Okay, they're rigid, the angles are rigid, and in fact, it's at such a low temperature that it's very difficult to have torsional motion or dihedral motion around the angles. Okay? And so in this case, what would W be? Let's say we have a very, very low temperature, and by low, I haven't really been very precise to say what low is, but we say we have low temperature, and so everything now is rigid. All internal components are rigid. Again, rigid is a word, it's not very precise, but you get for this, the point I'm going to make here is not about the rigidity of the temperature. So if everything is rigid, is it obvious to you what W would be in this case? Let's say we find the configuration to be this, and we look at it and, you know, at this temperature. So yeah, sorry, I interrupted someone.
I was thinking it was the W was just going to be 1, or the state of that it's in.
Exactly. That's exactly right, because we've said, right, the bonds are not going to lead to, the stretching of bonds is not going to create any more configurations. The angles are constrained, so they're not going to lead to any more configurations. And now we're saying that it's at such a low temperature that we're not going to have any torsional motions. So those are not going to lead to any new configurations if we were to find the configuration that I've shown here. So as Sheldon said, yeah, it has to be 1. There's only one configuration under these experimental conditions that we'll find. Okay, and we know that then S is equal to KB natural log of 1, but natural log of 1 is
0.
0. So the entropy is 0. So entropy, when we actually see and understand it at this very fundamental level, and this is the very fundamental level for an isolated system, okay, such as the universe, it has an absolute value. Entropy has an absolute 0. It has a value that has a 0, okay? Because when we find a system, and we can approximate systems that have very, very few configurations, W, okay, or the number of arrangements that they can be found at a very microscopic level, W can be 1, okay? Crystals, for instance, perfect crystals, that's a great example. Semiconductor industry uses perfect crystals, or tries to. You can have entropy be 0 or very close to 0. And in fact, entropy is the only state function, the thermodynamic state functions that we will encounter or that are known to have an absolute 0. Okay. No other of the thermodynamic functions has oops. S has an absolute 0. And this is an example of how it can and why it does. Okay, U does not, H does not, and as we will see later, the other things that we encounter don't have absolute 0 level or an absolute 0. So you can only talk about delta U's and delta H's. You can never say that, oh, there is a U, because that U will shift. There is no 0. I can, right? In all of our discussions so far of U and H, we didn't come up with an expression that says U is equal to something that I can compute that turns out to be 0. U is always going to be something that's relative to some reference point that we define. Likewise for H. But with S, with entropy, entropy has something that we can define very precisely to be 0. And it has a 0. Okay, and that's the only thermodynamic potential or only thermodynamic state function that is known to have this property. Okay, yeah, entropy is very unique in that sense. Okay, great. Any questions? Okay, what was I going to say? Oh, right. And so this expression is actually, maybe some of you know, is engraved on Boltzmann's tombstone. Actually, it's that important. And in fact, the form he called W, Boltzmann called W, this Greek omega, capital omega. And so on his tomb is KB natural log omega. And people didn't really accept this during his lifetime, as it always usually happens with breakthroughs in history and science. And sometimes even the scientists who come up with these things don't believe it. And that's the hallmark of a great scientist, skepticism. But this is what's on his tombstone. Okay, so there's one more interpretation of entropy that we can get from this expression, which I'm not going to start. I'll finish this up next class. But this is one of the things that I hope, again, for isolated system, such as the universe. Okay. I hope that you will always keep in mind for the rest of your careers in your life that this is really what entropy is. A beautiful, elegant expression. It's so simple, and that's really great things happen when you have in physics, when things come out to be so simple, but so powerfully insightful, right? And this simple expression speaks volumes, and it's so clear. It's so clear about what entropy is. You don't have to say anything about it. I will give you another probabilistic interpretation of entropy, again, starting with this expression next class, and then we will do some examples using, we'll do some examples to calculate delta S using the dq reversible over T expression, because that's really the traditional way in your textbooks that is introduced, and we will move forward from there. So any questions? I'm going to end today with this point. Or comments? Okay, in which case then, I really appreciate the input I got from lecture today. That was really fun. It's fun for me too. So I'm going to end the lecture, and I wish you all a good rest of the week. Okay, thanks.